So here, with our next exercise, it states the composition of adipic acid is 49.3% carbon, 6.9% hydrogen, and 43.8% oxygen by mass. What is the empirical formula? So take a few minutes to see if you can work this one out. Okay, pause the video if you like, and I'm about to reveal the answer. The empirical formula is C3H5O2. Okay, if you didn't get that, maybe go back and try again. It should be C3H5O2. Now, determining molecular formula from empirical formula and molar mass, a compound consists of 12% carbon, 1.1% hydrogen, and 86% bromine. Its molar mass is 186 grams. What is the compound's empirical formula and its molecular formula? So now we're determining the molecular formula as well. We know that carbon has, when it says C equals 12, H equals 1, bromine equals 80, what we're saying is carbon has a molar mass of 12 grams per mole, hydrogen 1 gram per mole, bromine 80 grams per mole. Okay. So here we have CHBr. Now if we divide the percentages by the molar masses, so 12% carbon, so it's going to be 12 divided by 12. Hydrogen is 1.1%, so 1.1 divided by 1. And bromine, 80, is the molar mass, 86 is the percentage, so 86 divided by 80, and we get ratio similar to 1 is to 1.1 is to 1.1. But if we divide each of those then by 1, why are we dividing by 1? Why are we dividing each of these three numbers by 1? We're doing this, if you remember correctly, we're doing this because we divide throughout by the lowest number that we get. So that way we're getting whole number ratios. So roughly what we're getting in this case is a 1 is to 1 is to 1 ratio. And you notice that these are off. Occasionally they're a little bit off. Now this could be because we're rounding, or it may be because the percentages have been rounded, or the molar masses have been rounded, or it could be instrumentation error as well. Okay, so quite often these are a little bit rough, and we need to, if they're very, very close to being whole number ratios, what we need to do is find that whole number ratio. Okay, if it was 1.5 or something like this, well then we know that really we're going to have to double all of them. But if it's 1.1, even 1.2, okay, we know that we just need to round these off to 1, for example. And we're given the empirical formula, so one of each, CHBr, that's the empirical formula. What we do need to solve though is the molecular formula. Okay, so we need to go ahead and solve that molecular formula. So the empirical formula is CHBr, right? Now, if we work out the molar mass of CHBr, that's 186. If you get a carbon and a hydrogen and a bromine, 12 plus 1 plus 80, that's, well, hang on a minute, that's not 186. What is that? 12 plus 1 plus 80 is not 186, but n times 12 plus 1 plus 80 will be 186. What is n? N is the number that we have to multiply throughout to get our molecular formula. Okay, so 12 plus 1 plus 80 is actually 93. So n times 93 will be 186. Okay, so what is n? N times 93 is 186. So what is n? N must be 2. Okay, so that means, as we multiply throughout, C2, H2, Br2. Here's our next exercise. So the composition of adipic acid is 49.3% carbon, 6.9% hydrogen, and 43.8% oxygen by mass. The molar mass of the compound is about 146 grams per mole. The empirical formula is C3H5O2. What is the molecular formula? Right. This is a very similar question, so maybe take a little bit to try and work this one out. So we've got C3H5O2, and we know that the molar mass is 146 grams per mole. Actually, we can work this one out together. Let's go ahead and do this one. Okay, so 3 carbons is going to be 3 times 12 plus 5 times 1 for hydrogen plus 2 times 16 for oxygen, and we should get 73 grams per mole. That's for the empirical formula, 146. So N multiplied by 73 will give us 146. So N must be 2. So that means the molecular formula must be double the empirical formula. We're not going to put a coefficient of 2 out the front. What we are going to do is double all of those subscripts. So we're going to get C6H10O4. Okay, I hope you were able to follow along. C6H10O4. What are solutions? Now, we're going on to a new part of the lecture now. So we're all finished with empirical formula and molecular formula and mass percentages. Now we're getting on to something completely different. We're discussing solutions and how we can actually make molar solutions in the lab. And we're going to be doing a lot of this in this week's lab. Okay, so solutions are homogeneous mixtures of 2 or more pure substances. The components of the solution may be ions, molecules, or atoms. The components of a solution are uniformly distributed. The particles which make up a solution are 1 nanometer or less in diameter. The small particle diameter means that such solutions as sodium chloride, air, copper sulfate are transparent. Okay. So let's look at some examples of solutions. We could have a solid dissolved in a liquid. So for example, sugar and water. We could have a liquid dissolved in a liquid. So alcohol and water. We could have a gas dissolved in a gas. So we could have the air that we're breathing, which is mostly oxygen and nitrogen. So what is air mostly made out of? It's mostly made out of nitrogen. And a solid dissolved in a solid could be something like metal alloys. Solute and solvent. So as far as a solvent goes, the pure substance present in a solution in the greatest amount. Okay, that is the solvent. It's the pure substance that's present in the solution in the greatest amount. Isn't that a strange definition? Okay, then we've got the solute. Now there is actually an exception to that rule. I'll get to that soon. Then you've got the solute, which is the pure substance or substances which are present in smaller amounts than the solvent. Okay, so these are present in smaller amounts than the solvent. So for a solid in a liquid solution, so maybe a salt or a sugar dissolved in the water, the solid is the solute and the liquid is the solvent. The water is always the solvent. So even if you've got a cup of sugar and you add a teaspoon of water to that and you make a very, very thick syrup, which you can do with a bit of heating and a bit of stirring, you make a very thick sugary syrup, you would still consider the water to be the solvent and the sugar to be the solute, even though the sugar isn't present in the greatest amount. Okay, so there's an exception to that rule, like I mentioned earlier. A colloid is a homogeneous mixture where larger particles than those in a solution are dispersed through a dispersing medium. An excellent example of a colloid is milk. Okay, so milk is a colloidal solution. It's not a true solution, it's a colloidal solution because the particles are a bit larger. The particles are so large that they scatter light and it might appear cloudy or murky, or milky if you like. So some examples include milk, of course, butter, paint, aerosol sprays, smoke, and some glues. The key thing about a colloid is that it won't settle out. Okay, so if you leave your milk sitting in the refrigerator overnight, you don't really need to shake it when you use it in the morning. You might like to shake it, but there's not going to be very much of a difference because those particles are so small that they're not going to settle to the bottom. Not very quickly anyway. So here's some different terminology. If something's soluble, that means it dissolves to a notable extent in the particular solvent. That's a simple definition. If it's insoluble, then it won't. The substance does not dissolve to a notable extent in the particular solvent. Okay? Here's a good point. If it's said to be insoluble, it does not necessarily mean that it is totally insoluble, because it might be 0.0001% soluble and the rest might be insoluble. And to the eye, to the observer, you would say, oh, that's insoluble, but really it is slightly soluble. Okay, so a better term to use is slightly soluble. And this is the term that we will use when we're looking at solutions later on. Slightly soluble. Really, it means insoluble. Okay. What about a concentrated solution? Well, it's one where a relatively large amount of solute is dissolved. So you could have some very salty water. You could have a dilute solution where a relatively small amount of solute is present, so slightly salty water. You can have a saturated solution where the solution contains as much solute as it possibly can and you can't dissolve anymore. So imagine you're adding salt to water and you're stirring it and stirring it and stirring it, and eventually you'll add one more spoon of salt, but it won't dissolve because the water has dissolved as much, that amount of water has dissolved as much salt as it can at that temperature. So that's a saturated solution. You can even have a supersaturated solution where a greater amount of solute then can usually be dissolved at a particular temperature. So, okay, how would this doesn't sound right, but how could you make a supersaturated solution? One method, there's plenty of methods, but one method that you could use would be to, perhaps with some sugar, for example, add spoon after spoon and stir it and stir it and stir it, and eventually you'll reach a point where there's just a little bit of solid sugar down the bottom of your container that won't dissolve. You could heat that solution a little bit, dissolve that amount that won't normally dissolve, and then cool it back down, and you'll find that the solution will remain. It will remain dissolved, and you'll have a supersaturated solution. But a supersaturated solution, they like to have a precipitate form. And this is how we can grow crystals in the lab as well. You make a supersaturated solution first. Usually you do that by heating and then cool it down. And then as it cools, you might have some of the solid coming back out of solution, okay? And it's going to form crystals, and those crystals will grow larger and larger over time. And in this way, you can form crystals from your supersaturated solution. Let's take a look at water and its use as a solvent. So water is special, okay? So it's got a particular shape, and due to this shape, and we've had a look at this very recently with our Lewis structures, due to this shape, it's going to be a very polar, very small molecule. It has a high specific heat capacity, which means it can hold a lot of heat. Okay, so your warm cup of coffee doesn't go cold very quickly. It actually holds heat for longer than most materials do. Makes excellent cooling, excellent for cooling systems. So think about the radiator in a car, uses a solution that's mostly water as a coolant, makes an excellent coolant because it can hold a lot of heat. An example of something that doesn't hold a lot of heat is perhaps aluminium. Okay, so aluminium warms up very quickly, it cools down very quickly, but it won't store that heat. Water's different. Water will hold heat. It's got a high specific heat capacity. Ability to dissolve things, it's unique because the molecules are so small, it's able to dissolve ionic solids, okay, and also non-ionic compounds as well. So ethanol, for example, if it's polar, it will dissolve in water as well. And, well, pure water, you may have learnt previously, pure water has a very low electrical conductivity, which increases sharply if you dissolve say, an ionic solid like sodium chloride, you'll actually get an increase in your electrical conductivity. Okay, so let's have a look at the nature of aqueous solutions. So a characteristic of aqueous solutions is its electrical conductivity. The degree to which a solution conducts electricity is dependent on the number of charged species. Alright, so some electrolytes are strong, some are weak, and we'll learn about this very soon, the Arrhenius ionic theory. So this is something that we're going to discuss quite soon when we're looking at pH. Here's an example of the hydration of an ionic solid. You can see that our ionic solid in a lattice is being dissolved by the water because the ions are able to be surrounded by those partial charges on the polar water molecule. So, as far as electrolytes go, you could have a strong electrolyte. Okay, you're going to get a strong electrolyte. And now these are electrolytes where you've got a complete dissociation. So, for example, let's have a look at hydrochloric acid here. Hydrochloric acid in water will completely dissociate into the ions, our hydrogen ion and our chloride ion. Okay? Then you've also got weak electrolytes which have a partial dissociation. And most commonly these are our weak acids or our weak bases. So here's acetic acid, so vinegar contains acetic acid, that's the acidic component of vinegar. When mixed with water, some of it will dissociate, so some of it forms a hydronium ion, okay, and a conjugate base ion, so some of it ionizes, but it's only about 1%, which is the reason why we put vinegar on our salad, but we don't put hydrochloric acid on our salad, because hydrochloric acid is a far stronger acid because it's got that complete dissociation. And this is something that we'll cover very soon. So how do we express concentration? Here's some general information on how concentration is expressed.